and I pick up again after omitting this Metz method on page number 19 on this NRG and DMRG issue. Once that is done, I will revert a little bit to one or two standard procedures with DMRG. You remember, or MPS rather, I left out one page essentially yesterday because we will need that for these infinite size algorithms I will be then talking about for the rest of the lecture today. So I assume not everyone of you is familiar with NRG, and I don't think there have been any lectures on NRG, so let me briefly remind you of what this is. This is actually quite a venerable old method going back to the 70s, introduced by Ken Wilson, got a Nobel Prize for his work on RG methods. So what it is about, it goes back to a problem which now comes under the name of Kondo problem, namely the problem of resistivity in metals. We will not talk about that, which have the following structure. You have some bulk. Just think about that like a Fermi sea of electrons. It's just or some formed from some s orbitals, something like that. And then you have a magnetic impurity. Somewhere in between. Very often this is very strongly localized by a d or an f orbital, and the minimal model to describe that is one you have actually already seen, at least in Philip Werner's talk, but probably also through the other 3 weeks I have been here. The minimal model to describe that, which has kept people busy for quite some time, excuse me, it goes back to Anderson. Oops. And it's simply formed in the following way. You sum over momentum and spin, and then you have a band epsilon k, c dagger k sigma, ck sigma. So this is the band. And then you have the possibility of electrons hopping from one of the band orbitals or states onto the impurity and back. So you can hop from either any momentum state with an amplitude vk, which is called the hybridization function. I call the localized orbital on the magnetic impurity, I call it f. So you get an f dagger sigma, ck sigma plus the Hermitian conjugate. And then last but not least, what makes the problem interesting is that the impurity can be occupied by up to 2 electrons, one spin up, spin down, and if they are doing that, because it's a very localized orbital, they will strongly repel each other. There are various ways of writing this. This is the so-called symmetric form, so I count the number of up electrons times the number of down electrons, and people like sometimes put this factor -1/2 to make the model symmetric, but you know, it's nothing profound going on there. So NRG is about solving this Hamiltonian, at least when it comes to understanding how the impurity interacts with the rest of the system. And NRG basically is a very complicated set of conceptual steps, and very often in discussions about it, people only focus on the last one. I have to basically talk about all of them to make the relationship to DMRG clear. And what NRG does is, in a first step, which I will not give in all details, it turns this into a tractable model, which in the second step is then dealt with by a numerical method. So there are many steps, and one of them is that you assume that this is an S-wave orbital, so everything is isotropic. Then you can reduce that problem to a one-dimensional problem, essentially using the density of states. You transform that from a sum over momentum to an integral over energies. And what you then end up with is your original Hamiltonian with an integration d epsilon, and I take a rescaling of the energy band so that it just goes from -1 to +1. That doesn't really make a big difference. I still have the sum over the spin. Then I have a model density of states, which here I just take to be epsilon. There again, you could put something different, and I get C dagger, C epsilon sigma. And of course, if you go from the CK sigmas to C epsilon sigmas, the hybridization term has to change too. So this becomes a sum over sigma integral d epsilon, d epsilon. And then so like you introduce something weird which has the form square root of delta epsilon over pi, and then you have your F dagger sigma C epsilon sigma plus Hermitian conjugate, and then of course you still have the term on the impurity itself, the repulsion term, which I will not write out. Okay, so the hybridization function here is delta epsilon is simply given by looking at that and seeing which momenta match actually the energy. So what you get is, this is a sum over all the momenta, delta epsilon minus epsilon k, vk, and then introduce a factor of pi, which I'm dividing out here again. Okay, so this is a standard procedure. Let me also assume that we are at half filling, meaning that the Fermi energy will be at energy 0 in this picture. And what people already knew before Wilson, mainly due to work due to Phil Anderson, who did something on this model which he called the poor man's scaling, from which you could see that the physics of this problem essentially happens close to the Fermi energy, which here would be around 0, as I mentioned, and that the contribution of states around energy 0 would become exponentially more important compared to the ones at high energies. This follows from this poor man's scaling, which certainly many of you have seen in solid state classes. Otherwise, you just Google it or find it in any textbook. But anyways, Wilson was motivated by that to say, well, if what matters is really happening close to 0 energy, then I take my entire band. I'm now plotting here energy epsilon, so the story is happening here at 0, and I divide my band into parts which are not so important and which are more important, and I do it logarithmically. And what he did is he introduced something called the hybridization parameter. No, discretization parameter, sorry. Which he took originally to be 2, and that's still a quantity you usually take. And then what you do is you divide the band here from 1 to lambda over 1 over lambda here. Then you take, which is 1/2. Then you take this 1/2, you divide it again, so you get lambda minus 2. Then you divide that again, that again, that again. And you see the whole thing becomes exponentially dense around 0. And the whole thing you do from -1, minus lambda, -1, -2, -3, 4, 5, 6, and then my drawing fails me. But anyways, so like these are energy intervals. And with a bunch of approximations and transformations, for which I refer you to either Wilson's Review of Modern Physics from 1975, which is really a landmark paper of physics, which is always worthwhile reading. He does it there for a spin model, not for the electronic model. If you want to see it for the electronic model, there's a paper by Krishnamurti, Wilson, and Wilkins in some order, which is a PhysRev B of 1980. So if you Google Wilkins plus Wilson, you will find that. Fortunately, I didn't write down the reference. But so like, and there is a review of modern physics by Brusch, Gebulla, and Kosti, which was in Reviews of Modern Physics. I think it was 2009 ±1. Yeah, Well, I read the preprint and then I didn't really bother to download it again, but it's very good. It gives you all these details which I will not give if you want to become an NRG aficionado. And what happens is the Anderson Hamiltonian, after all these things, takes a form which is 1 plus lambda to minus 1. Doesn't really matter too much. But here comes the interesting thing. It's a sum from n to infinity. Of course, also a sum over spin. Lambda to minus n, and we will be interested in that. And then it basically gets a and sigma dagger a and sigma, so a density operator minus b and sigma b and sigma. And this corresponds to the states of energy above 0. And this corresponds to energy less than 0. This is why it gets a minus. So this is the band now. Then this band couples to the impurity, and there you get some expression plus psi 0 over pi, sum over sigma, f dagger sigma, and this couples to one orbital which I call d now, d0 sigma plus Hermitian conjugate, and then again the u term which just stays as it is. And the important thing is this d orbital is constructed. I will simply write it down so that you have the complete formulae, but let's not worry too much about how you obtain that. That would actually be 1 to 1.5 lectures to derive it. C epsilon sigma, and this is just essentially to get the orbital normalized and to have the usual commutator relationships. And in the special case where you assume that the hybridization function doesn't really depend on energy, which people often do because somehow it really influence results too much, then you can work out that this psi 0 is 2 delta, and the delta 0, that's actually the only formula that really matters now. The delta 0 sigma is given by this 1 over psi 0, and it's the infinite sum of these A and B operators, A and sigma plus B and sigma with some prefactor, which you can read up in the literature, which means, and that's why I say this is the one important formula here, if you look at this Hamiltonian now, what you have is the following. Let me represent it in a picture before it gets too confusing. I have here the impurity, which has this on-site interaction U, and then the impurity couples to this orbital D. Now this orbital D is a superposition of all orbitals A and B that we have introduced to the band. So it couples to all of these guys. Like A0, B0, A1, B1, and so on and so forth. So perhaps you're not surprised to learn that this is called a star geometry. And these objects, of course, at the ends here, they have their density-like term, which we have written up for the band here. And the interesting thing is the weight of both the coupling and the hybridization goes down exponentially. It's easy to see that the density gets a prefactor lambda to minus n. So from here they get exponentially less important. And what is not so obvious, and which you just have to believe me now, is that these guys go like lambda to minus n over 2, so they also go down exponentially. Which means that what matters most is this guy here, then this one, then this one, this one, this one, this one, and they get less and less important. Okay, so this is what Wilson arrived at, and while this may look like a relatively simple structure, I mean, you may argue, well, you essentially have a non-interacting stuff here, then they hop to each other, but these hoppings are not related, and that should be an easy model, but unfortunately this still cannot be solved, And now comes the last step of Wilson, and then we are done. What he did is he took this Hamiltonian and he took the part except the interaction. Then you have a non-interacting model which you can write down as a single particle problem. And for the single particle problem, what you can do is you can do a Landtröss diagonalization of the Hamiltonian matrix that you can write down for the single particle problem and bring it into dry diagonal form. You can do that for any matrix. So what Wilson then obtained is, after this mapping to dry diagonal form, and then we get into our business. Landtröss, we obtained the following Hamiltonian. Still the Anderson Hamiltonian. There's no further approximation involved. So here is the coupling term F sigma dagger D0 sigma plus Hermitian conjugate. Nothing changes there. But these guys are totally reshuffled into new operators. And the whole thing takes the form sum over n from 0 to infinity, and then of course also a sum over the spin degree of freedom sigma, a hopping term Tn, and then you get Dn sigma dagger, Dn plus 1 sigma plus Hermitian conjugate, and then of course still our interaction term u, which we still carry around. So there is a formula in the handout on page 21 for this Tn. The important thing for us is that this Tn is proportional to lambda to n minus n over 2, which means that we can represent this problem now in the following way as a semi-infinite chain. We have the on-site interaction u here. Then we have a coupling, or you could interpret it as a hopping term, psi 0 over pi here. And then I have T0, T1, T2, T3, T4, and so on. But I have no interaction here. Okay, and these guys decay exponentially, which means that it's reasonable to expect that at some point you can simply say, well, let's stop here. Say after 100 hoppings, they are to the power of, say, 2 to minus 100, which is, what is this, 10 to minus 30 or something like that. And 10 to minus 30, when the typical energy scale is of the order 1, you definitely can ignore. Okay, so and that shows that we are now into the business where we can talk about relationships to methods like DMRG, because this, of course, if you ask, well, what's the ground state of this guy here, you would feel, well, that's something you can definitely do by DMRG. But before we talk about that, let's first see what Wilson did about it. And I don't know whether I will go with you through the full beauty of that. I think everyone has the handout. I will focus on those formulae that matter for what I want to discuss. Wilson set up a very complicated, well, a very beautiful and complicated RG procedure, which is on the top half of page 21, basically in the box. He set up Hamiltonians for increasing parts of this chain, which he would then call Hamiltonian Hn. And then, of course, the total Hamiltonian would be that one taken to the limit n to infinity. And because he wanted to keep similar energy scales numerically, of course, he took into account that because everything goes down by these powers of lambda to minus 1/2 at each step, he rescaled them. And that's the typical energy rescaling step you would do in an NRG procedure, including NRG. Okay, and so that allowed him to set up typical RG flows, as you know from field theory lectures or stuff like that. but I will not focus on these RG flows now, and so that's why I'm not writing it up on the blackboard, but I'm now worrying about how did he actually solve these Hamiltonians, because I mean, it's nice to set up scaling properties, but you need to know something about, for example, the spectrum of this Hamiltonian Hn here, and that brings us now to what most people refer to as NRG in the narrow sense of the word. So what he did is he said, well, let's fix some number which I call uppercase D, which could be of the order of 1000. That would be a typical value for present day NRG calculations. I use the letter D because we will see that it's exactly the, the quantity that people like Frank like to refer to as uppercase D. Steve White, I think, still likes to call it lowercase m. I sometimes use uppercase m, have switched to the D notation, and Ifra Vidal likes to call it chi. It's always the same number, so just that you know when you go through this tensor matrix, whatever literature, when any of these four guys shows up, they always mean the same, at least in one dimension. Okay, and what Wilson did is he fixed a chain of the length where the number of states, if you write it down exactly, is still covered by this number, say 1000. So he chose it such that he could still diagonalize the Hamiltonian on that system exactly. Okay, so once he had done that, of course he would obtain states. And in the way I call it, sort of like the Hamiltonian, if it's the Hamiltonian of a system of length L, it's called L minus 2, simply because this side is called side 0 and this side is called side minus 1. But don't worry too much. The only thing that really matters is what happens now if I add one side, namely extend my Hamiltonian by one of these guys. Then sort of like here, these will be states sigma on, say, L minus 1. And there will be 4 of them, because it's an electronic problem, spin up, spin down, empty double occupancy. And so you now move to the next bigger system and diagonalize that guy. So what you would obtain is states M L minus 1. But the problem now is, instead of having, say, D of these states, you now have 4D. And if you continue like that, of course, you would be in an exponential growth problem of the number of states, 16D, 64, and so on. So what Wilson had to do is he had to somehow limit that growth. And he said, well, I truncate it back down to D. And the truncation procedure he gave, and this is exactly the one decisive point about the procedure. I wrote up all this stuff about rescaling, but for our purposes, the one thing that matters is he said, keep the lowest energy states. Why that? The reason for that is a very good physical background, because he would argue that, as we knew already from Anderson's arguments, the important physics is the one at zero energy. So what matters is not what's going on here so much, or going on here, but what matters is what's going on here. Okay, so that's why we could focus on low energies. But then you could argue, well, but there will be further energetic contributions that might mess up your spectrum, and then the choice you made is a bad one. Here the argument of Wilson is, well, look at the couplings. The couplings are going down exponentially. So the correction to the energy spectrum you get in this region here will be smaller, and yet even smaller. So by a separation of energy scales, you can argue that the contributions that will come from later parts of the chain, which are added in that procedure, that these contributions will only basically be something like perturbative corrections you can ignore for the time being if it's about the question of which states you choose. So for like later contributions, only essentially perturbative. When it's about the energies, I mean, I have to be very careful here because the physics of the problem, if one sets up the RG procedure while you're moving through these energy scales, will change completely. That's not what I mean by perturbative. By perturbative, I only mean that sort of like when I ask the question, is it a good idea to keep the lowest energy states? And if they say yes, it is, because how these will be wiggled around by later contributions, that is definitely only on a perturbative scale. So what Wilson achieves in that way is by always keeping the lowest energy scales and doing his rescaling of energies, he is focusing more and more closely on everything that's going on here. And that's basically what he does. You can check the quality of your calculation by varying this number of states d. You can then look at how these energies, these eigenstates flow. Then you can define RG flows, nice things like that. For this, I really refer to these to this literature because, as I mentioned, NRG would be a whole topic of several lectures on its own, which we cannot do. But what we can do is, without understanding too much about this thing here, is to say, well, does this relate somehow to DMRG? Obviously, these new states, ML minus 1, are a linear combination of ML minus 2, sigma L minus 1, ML minus 2, sigma L minus 1, ML minus 1, and then these states here. And the procedure of Wilson is encoded here. And what we can also do is we can, and now I think you will see what I'm aiming for, we can say we introduce a set of matrices A, and we introduce lowercase d of them, one for each value of sigma, which means we would get 4 of them, matrices A sigma L minus 1. And we would identify row and column indices like M L minus 2, M L minus 1, and fill this matrix by these entries here. Okay, and what you now see, of course, is that the whole thing can be recursed through this entire procedure. So what you have is that in the end, your state M, say L minus 1, is something like a sum from sigma minus 1, sigma 0 to sigma L minus 1. Don't worry about the fact that the numbering is a little bit weird in this whole thing. I think I did not care about it in my notes. So A sigma minus 1, A sigma 0 to A. It would start at 0. So, sorry, sigma minus 1. A sigma 0 to A to sigma L minus 1, sigma minus 1 to sigma L minus 1. Okay, and I mean, then this thing here, it starts with a scalar times, it starts with a vector times matrix, like in any matrix product, same with open boundary conditions. So you get a vector from this product, and then I simply take the index ML minus 1 out of this product, and this is the state here. Okay, and that's what you get. If the whole thing ends at some point, you really have obtained a matrix product state, and the ground state would be given by picking the component 0, 1, so the lowest energy one, here at the end. So, but what you hopefully learned from earlier lectures is that what DMRG does, with small qualifications, depending on how you set up the sweeping process, is that it finds the variationally lowest energy state in an ansatz class like this one. I think this was covered. Yeah, okay, good. So, but this means that if your question is that you want to find for this Hamiltonian the lowest energy state, well, then definitely the best way of doing it should be DMRG. So from that point of view, you can already make the statement, without actually looking at any detailed calculation, that by definition, being the variational optimum, DMRG must be able to give a better choice of A matrices for the problem at hand than Wilson's lowest energy state prescription would give. Okay, so the question is this being optimal much better than Wilson's NRG? And the answer is, well, if you're interested in this Kondo problem, what is going on around zero energy, where, for example, in a calculation of the spectral function, people would find the following result. Here's the omega of the spectral function. It's the spectral function of the electrons on the impurity side. Then what you get is you get a peak by around -u, which is not very pronounced. Then you get a very sharp resonance, the Kondo-Suhl resonance at 0. And then you get another of these bands here. And the interesting impurity physics is all happening here. And it's a tribute to Wilson's genius, really, one must say, that the choices he made are so clever that if you do it with DMRG instead, you will not really improve much, or in any way that, well, I will lose any second sleep about. But the interesting thing is that where you can definitely improve things is away from the zero. So like the improvement will be here. And why is this? Because NRG is basically like the first step of a DMRG calculation when you set up your system before you improve your result by the sweeping. Because what happens is sort of like the choices you have made for this part of the chain, they will never be affected again by what happens later on. So the information flow is totally unidirectional in NRG. Whereas the sweeping procedure you set up in DMRG to improve the choice of these matrices here means that information can now flow both from high energy to low energy and back. And this is what NRG cannot deliver. And the point is, because you start calculating at very high energies, because the big hoppings are around here, the information you have here, which is at the bigger energies, will not be influenced by what you learn later on from NRG here, whereas it will be influenced in the case of DMRG. But as the really interesting physics is happening here, you could argue, well, maybe this is not so interesting. But what I claim is that nevertheless, if you move beyond standard applications of NRG, where this is a masterful technique that has been developed for the last 35 years, you can make easy gains by using DMRG. The first thing, for example, you could do is that if you go back to Wilson's argument why he could do this lowest energy state truncation, it was because of the separation of energy scales. The separation of energy scales was ensured by writing the chain like this with this parameter lambda, which made these energy scales go down exponentially. Your solution to this problem would become better and better if you let lambda go towards 1. 1 would mean that all energy intervals would become of equal size and equal quality, and you would not just focus on the information here. But if you do that, if you push lambda towards 1, the separation of energy scales argument will break down, and so will NRG. In DMRG, where because of the sweeping information is not just flowing one way, but both ways, there is no need to do something like a separation of energy scales to make the method work. And one very simple application, which is still in a very trivial model, but which makes NRG fail completely, but makes DMRG work extremely well, is that you take the Anderson model, where your metal which we had originally with its magnetic impurity, and you expose it to an external magnetic field. What happens is, well, there's some simple intuition is that if there's a magnetic field which gives different energy scales to spin up and spin down, what you expect is something like that the spectral function upon introduction of a magnetic field B will, well, there will still be these so-called Hubbard bands, but then the peak structure will split up into something like this, which depending on which G factors you have, this will split up by a factor of B something. Okay, but now if you're doing your logarithmic discretization to get your energy scales sorted out as you need it for NRG, all your information basically will be concentrated around here, and what NRG will produce for this peak here is, essentially it will simply not see it at all. It will produce you some very undistinct structure in the spectral function which looks like that. If you do the same problem with DMRG, and because you have a rough idea already where the peaks will sit, you may say, well, I'm not interested in these guys here, but I make my I make my grid relatively dense here, and I keep it like that, and out here nothing is happening anymore, so I make it wider again. So in NRG you would not be able to do that because you're abandoning the separation of energy scales if you sort of like keep them roughly of the same size. In DMRG this does not matter, and these peaks emerge beautifully in the calculation. For looking at the detailed picture, I would just refer you to the paper I give in the literature list on these calculations, which we did this calculation a long time ago, but until the whole thing got published, it was just 2009. Okay, but anyways, this is the first thing, something really simple that NRG could not deal with. The next thing you can do is you can be much, much faster than in standard NRG for the following reason. If we look at our chain, we have these sites where you can have spin up and spin down. So give you 4 states. If you look closely at the Hamiltonian here, you see that there is no interaction whatsoever between the spin up and the spin down electrons, except the one which is mediated through the repulsion, which is just happening on the first site here. So it's a reasonable assumption, and in fact it turns out it's quite true, that the interaction between the electron sitting here and the one sitting there is very weak. So the induced interaction, to be more precise. Induced interaction is very weak. But this means that essentially you are simulating something which you could also, in a rough approximation, draw like this, that you have your impurity and 2 semi-infinite chains stick out from it, one which has just spin up, or is empty, and the other one has the spin downs, or is empty. And they barely do not interact. And one thing which I mentioned also yesterday, which was the reasoning why the Metz method is so interesting at very low temperatures, if DMRG takes of the order of d states to simulate a chain like this, and then because they're symmetric, will also take these states of simulating something like this. And if they are not, or if they are essentially not connected, forget about that side for the moment, then the number of states you need in a DMRG simulation is d squared. So, and in NRG, you have to treat these guys together because they are sitting at the same energy scale, and you have to treat the same energy scales at the same time. Otherwise, you would violate your separation of energy scales and the whole thing breaks down. So, if you interpret it as a DMRG-like algorithm, for a given precision you want d squared states. Okay, now if you do it with DMRG, you do not worry about the separation of energy scales anymore, and you can simply read the whole thing as a chain which goes like this. The blackboard is not big enough now for me to unfold it really on the blackboard, but what you would get is a chain of double the length, where you would only have 2 degrees of freedom here, and you need roughly d states to describe it. So the numerical effort, where in NRG you needed d squared states, in DMRG you get away with roughly d states. Which means that to have the precision, which in NRG you need 1000 states, here you get away in DMRG, if you do this unfolding trick, with something which would be of the order of square root 1000. So let's say 32, and in practice it turns out you add a factor of 2 or something. So here in fact it would be something of the order of 60. And given that the calculational effort of DMRG and NRG, these are matrix multiplication methods, scales as the third power of the number of states here, you see that you gain an enormous amount of efficiency in your calculation, which NRG cannot give you. So, well, I mean, think about that. You have a factor of, which is still a factor of, say, 15. You take this factor of 15 to the third power, you're at 200 something. Well, you have to do a little bit of this DMRG sweeping, but it's actually not too much, so you're still faster by a factor of, I would say, 20 or something at least. And if you go to an even more precise calculation, the difference will become even more striking. So this is why people are at the moment, well, sort of excited whether DMRG could replace NRG in many of these applications. Because what you could also do is, if and that's something which we had hoped to do something meaningful, but I must admit that the calculations turned out to be extremely difficult, so at the moment I'm a bit demotivated, but perhaps we will get back to that. The idea we had is, because this is the last thing I want to say here, let me put it up here. In NRG you sometimes get the problem that you couple to several bands of electrons. And because of this separation of energy scales argument, you have to treat all these guys at the same time, which means that the size of your local state space grows exponentially in the number of bands. In DMRG, you would have the hope that you say, because it doesn't really matter to treat them at the same time, to unfold these guys to something which would look like a, say, star geometry, and then you would simply do your sweeping, sort of like moving around like here. You have to worry a little bit about the fat side in the center. But at the moment, I must admit that the numerics really beats us a little bit here. But I feel it could be that when computers get a bit more powerful, because we are not really in an exponential sort of problem, that could be an interesting alternative, in particular because you have easy access to real frequency quantities by time-dependent DMRG or something like that. But that's sort of like the dream people would have in pursuing NRG in the DMRG framework. What definitely already works is that in something like the single band picture, you can decisively improve on the results of NRG. That's already working. For the rest, I'm skeptical for the moment. One entire PhD student was burned for that, but so we'll have to see what happens in the future. Okay, good. So this was the part on DMRG meets NRG. In this second part of the lecture, I will talk about how to set up infinite size algorithms, because this is something which is sort of like the unloved little brother of normal DMRG, that when Steve White invented it in '92, he had this algorithm where you grow a system from basically nothing to the size you want, and then after that you do the sweeping to improve your result. And in the beginning there were lots of DMRG papers who thought that this sweeping was only some little add-on, and the real DMRG is this growth process in the beginning. Then people realized that the variational nature of DMRG is related to the sweeping, and this beginning is only a warm-up. And then people basically dismissed it out of hand. And so it's the unloved little brother somehow. And it's a more recent development of the last couple of years that people, well, rediscovered and actually perfected that you can do very nice things with this infinite size DMRG, which just grows your system as long as you want. So that's what I want to do now. you go. Let me postpone again this little technical remark which was missing on pages D and E, depending on how far I get here, because we will actually need it rather towards the end. So, what about these infinite size algorithms? As you have certainly seen by Steve, what he does is he builds up these blocks by sort of like inserting two new spins or sites here into the center, and then you build the next bigger block by integrating them into the older block into the old blocks, and then you go on, and like this, the system grows all the time. Okay, and well, I want to sort of like re-investigate that thing and do the following thing. The first thing, I introduce a labeling. Because of the way the whole thing grows, it's best not to think about the sigma 1 to sigma L notation, but one which I call sigma 1 on the left-hand side, which I call A, which sits here. Then comes sigma 2A, which sits here, and so on and so forth. So here we would be, for example, at sigma A lowercase l, and here I start from the right, sigma 1b, sigma 2b, sigma lb, which means they simply get the label by the order in which they were inserted into the center of the chain. So let's analyze the first two steps of such a procedure, because then we will recognize the law right away. Let's start with a block length of 0. So we just have these two sides. Which means that the wave function, which I call psi1, will be simply a superposition of sigma 1a, sigma 2, sigma 1b, psi sigma 1a, sigma 1b, sigma 1a, sigma 1b. Okay, so I minimize the energy of the Hamiltonian. I choose psi1 to minimize the energy of the Hamiltonian. So, and that gives me the psi sigma 1, sigma 1. So I obtained by energy minimization. I mean, for a two-side problem, this is still very easy. So what do I do with this guy? From psi sigma 1a, sigma 1b, I form a matrix, sigma 1a, comma, sigma 1b. I subject that to a singular value decomposition, u1, lambda 1, v dagger 1. I omit the indices here. And then I write down my A matrices, A1, sigma 1. I give you now a double index. The one says which spin am I referring to pick the matrix, and the one in the brackets tells me at which stage of the process did I obtain it. Unfortunately, this distinction is necessary. So A, and here's it's still a vector on the first side, so it's 1, comma A1, and this is just our matrix U1, sigma 1A, comma A1. And similarly on the right hand side, you get B1, sigma 1B, A1, 1. It's a column vector. It's V dagger 1, A1, sigma 1b. Okay, and from the properties of the singular value decomposition, you can show that these matrices A and B, which I have just introduced, are indeed left and right normalized matrices, which is why I'm justified to call them the way I do it here. And then you can introduce a fancy way of writing your state psi1. Psi1 would then be still the sum over the sigmas here, which I omit. and then you get A1, sigma 1A, lambda 1, B1, sigma 1B, and here I get my 2 sigmas. Okay, that was the first step. And now we just look at the second one, and then we are done. Let's do block length 1. So you have 4 sides. And what you do is, of course, you have a description of the block of length 1 here and of length 1 here. But what will change if you introduce 2 new sides is that, of course, this guy here in between, this lambda 1, will go away and be replaced by something else. Namely, psi 2 will get the form that I have to sum over sigma 1a, sigma 2a, sigma 2b, sigma 1b. I mean, I simply start building up the chain like this. I have this a1, sigma 1a here. Then I have something called psi, sigma 2a, sigma 2b, b1, sigma 1b, and then come the 4 sigmas, which I will not write explicitly here. So this guy here can be interpreted as a matrix. It just has to match the matrix dimensions of A and B to be multiplied into the whole thing, and I obtain it again by energy minimization. This is just like in standard DMRG. Okay, and now I think you know what the procedure will be like. I will take this thing here, which will have, I call it, the dimension it has to the left, I call A1A, and the dimension it has to the right, A1B. And then I do a reshaping of this matrix. I transform this guy here into a matrix where I put A1A, sigma 2A on the row indices and A1B, sigma 2B on the column indices. I can do that. That's simply a rearrangement of d squared matrices psi into one big matrix psi, like yesterday when we did the singular value decomposition trick to make it orthonormal. Then I do an SVD on this guy, and I obtain psi 2 is u2 lambda 2 v dagger 2. And then that's the last thing I write down here. I do a2 sigma 2a, a1a, a2a is u a1a sigma 2a, a2a. And the a2a comes, of course, from the sum I have implicit here, where I multiply the lambda to the guys to the left and the right. And similarly, and I think you take that from the notes, you get the expression for the b. And the psi 2 then looks, of course, like the sum over all the sigmas, a1, a2 for the precise indices up here. I would refer to the lecture notes, lambda 2, b2, b1, and here I get all my sigmas. And now you see how the whole thing will proceed. If I am at the nth step, you will have a sum over all your sigmas. You will have a1 to al. You will get this lambda L in the center. You will get BL, B1, sigma. Okay, so that's what infinite size DMRG does. You can represent it graphically, again, by the picture you already know. Here I have these A matrices, here I have the B matrices, and at the center, I will show that by a diamond. I have this lambda matrix extra, which is actually here diagonal, but that will not be necessarily the case, but here it is. Okay, that's what happens And this thing here would be my left half A, and that would be the right half B. So, okay, if you have that state, you can evaluate this state like you did, in finite size DMRG. You calculate expectation values by writing down these contractions, sandwiching the operators from the top. At the bottom, what you also see is that for some calculations, as I mentioned yesterday, it may be advantageous to have this mixed canonical representation of left normalized matrices on the left and right normalized matrices on the right. This came out here basically by construction without doing anything specific about it, so you could even argue that that looks like a nice state to have. But there are two questions which I would like to ask here, because this is something Steve White did in a different notation now 18 years ago. So, but we can do better, and we can do better by asking two questions about this thing. As I mentioned here and here, I said, well, obtain these psi's by energy minimization. Okay, in practice, when you do a DMRG calculation, these matrices you have to find here are really huge, and the Hamiltonians you get are huge too because of the number of states you're keeping in the DMRG calculation. So what you need in order to obtain this is some large sparse matrix eigensolver in practice. This is what it amounts to, and I'm sure Steve has shown you that at some point you need a matrix eigensolver. And the point is, eigensolvers like Lanzos or Jacobi-Davidson, which would be the two that are most used, basically start from a guess solution, which in the worst case is just a random vector, and then iteratively find their way to the true solution. Okay, then of course it would be a very good idea to have some prediction that allows you to make this process very fast. In finite size DMRG, Steve White invented a procedure in '96 to do that, which basically expressed the reduced basis transformations you have in DMRG for your state to make some of these sites free and put others in a block. In some sense, this was a very easy thing, and if you write it down in a matrix product notation, actually this prediction algorithm of Steve is totally implicit in a matrix product ansatz. For the infinite system, DMRG attempts to predict the next psi have been made over the years. For example, I put a paper which used the Marshall sign rule, and then it didn't work for frustrated systems, for example. That helped a lot, but it was extremely limited, and no one really had a clue how to do it. And it was Ian McCulloch who in 2008 found the solution how to do that properly. So how to make a good prediction for the next psi. And the second question you would like to ask, and this actually goes back to work by Ostlund and Romer in '95, that you really take this approach seriously, not just as a build-up to something where you start sweeping, but say, well, can I push this to make the system bigger and bigger and bigger and learn something about the thermodynamic limit state? That would be nice too. But of course you would like to do that without doing a million iterations, but somehow stop earlier. And the answer to both questions is actually given by exactly the questions at the bottom of page 29. The answer to both questions is essentially given by just one insight in the whole thing, because what you would like to understand in this procedure is if you want to make a chain for which, like this one, for which you have a state representation like this one here, if you want to add two sites somewhere here, what do I have to put into this state here? I mean, I will have to put in new A, lambda, and B matrices somewhere around here to basically make the prediction of psi L plus 1. What would this have to look like? And to answer this question, it's useful to simply identify what is the structure of the state that sort of like keeps repeating one after another. Of course, only in the thermodynamic limit, because in any finite system, these structures will be different because they are at different distance to the end. But in a truly infinite state, which is translationally invariant, at least up to some period, you would expect that here the same repetitive structure comes up again and again. So if you look at this state here, I would say it's very hard to identify it because you have these A's everywhere here, they are all different, and then you have this anomaly of the lambda sitting here, and then you have these B's with a different normalization. I mean, if there are ways of arguing your way around and identifying this unit I'm aiming at, but I do something different. I switch briefly, although I avoided it completely in these lectures, to the notation of Giffre-Vidal, where this is much easier to see without lengthy discussions. So I go to the Vidal notation, or some people also call it the gamma lambda notation, which is nothing but saying I take this state, but I keep the lambda explicit everywhere. You know, it was explicit for lambda 1 here, it was explicit for lambda 2 here, and here it's explicit for lambda L. It's sort of like these lambdas have not disappeared, sort of like the lambda 1 sat somewhere here, then there was the lambda 2, and so on and so forth. Can I make a notation where this is still explicit? And what Giffre did, and there are various ways of introducing it, is simply to say, well, I replace this guy here by lambda L minus 1 times gamma sigma L A. So this is a diagonal matrix lambda from the singular value decomposition, and this is some matrix set gamma with index sigma, so like the A's here, which also have the same index sigma up here. And the way I obtain them is, I mean, there are various ways of doing it, but if I do it like, and don't worry about mathematics and numerics too much, I just do the calculation as I explained it to you, and after each step, when I have my new matrix A, I say, well, I divide out this matrix lambda L minus 1, I remember it from the last step, to obtain this gamma. So I would have the following relationship, that lambda L minus 1, and I give the indices explicitly A, gamma sigma L A, AB is A L sigma L A AB. So you can get this guy here by dividing A through this object here. There's no problem in doing that in mathematics. On the computer, this is a bit of a horror, because singular values can become very small, and then you do one of these numerical no-nos to divide by very small numbers. But for the purpose of the notation, this is perfectly okay, and we can do the same thing here, of course, on the right-hand side, that I say, instead of the BL, I write a gamma L, which I obtain by dividing out lambda L minus 1, which I still remember from earlier iterations. So we would have gamma sigma LB, AB, lambda L minus 1 is equal to B L sigma LB AB. Yeah. What this means is, if you do that, that you get your state psi L in a notation where you sum over all these sigmas as before. Then it starts with gamma 1, sigma 1a, lambda 1, gamma 2, and so on and so forth, lambda 2, until you end up at gamma L and lambda 1 and gamma 1 on the B side. So if you make a picture of that, what you obtain is you get the same good old picture for a matrix product state. But where these guys here, which were previously the A and the B matrices, they are now these gamma matrices. And everywhere in between, we have sitting one of these lambda guys. And what you can see now, if we assume a translational invariance by at least a factor, by at least two sides, maybe it's even translationally invariant by one side, the repeat unit you would get, if you want to build, at least formally want to build up a state like this, would be a sequence of 2 gamma lambda. So we can write down the repeat unit, and of course the repeat unit, which will be close to what you would have in the thermodynamic limit, is of course the one that sits in the center and is most removed from the ends. So I would say the repeat unit is lambda L minus 1, gamma L, sigma L A, lambda L, gamma L, sigma L B. This would just be the repeat unit. And now I can, simply by using my translation rules, I can identify the repeat unit I would have to put in the AB notation, which would be, okay, this guy here is AL, sigma LA, lambda L, and this guy I can translate into B by B L sigma LB, dividing out the lambda L minus 1, so I would get lambda L minus 1 to the power minus 1. And at least to my taste, arguing why this is the repeat unit staying totally in the AB framework is a bit more complicated than taking it from this notation here. But anyways, this is what you would have to chain together to basically build up something which can be considered a translationally invariant state, which has a meaningful approximation to the thermodynamic limit, as long as L is already quite big. I mean, at the beginning, you're mainly talking about what's happening at boundaries. So, once we have identified that, we can answer right away 2 questions. The first is, how can we make this method extremely fast by predicting the next psi? And what I mean by faster is roughly the following. Typically in Tensor, when you find a ground state, the number of iterations you take in DMRG is 50 to 200 if you have no prediction, if you just start from a random vector. I mean, there are special cases where it's even worse or a bit better, but that's a ballpark estimate. If you do this prediction thing, which I will derive now in a second, for relatively short systems, you are already down to a few tens, and when your system gets appreciably bigger, we are talking about less than 10 steps. And because this is the part of the method that consumes essentially most of the time, to speed that up by a factor of 10 or more, that's definitely helping you a lot. So, what I do is, I simply take this state here and write down my guess for psi L plus 1. What do I have to do? Okay, I have to sum over all the sigmas. There are, of course, now many more of these guys. I come starting from A1 to AL minus 1. Then I put the center, which I already had, AL, sigma LA, lambda L. Then comes BL. But now the spin, which will sit now on the next longer side, will no longer be sigma LB, but it will be sigma AL plus 1, because your system is growing at the center. So it's sigma L plus 1A. Then comes lambda L minus 1 to the power minus 1. Okay, that's sort of like the first repeat unit. This is nothing new. Then I put it a second time to introduce 2 new sites. So I put AL. This will now be the new site B, sigma L plus 1B in the notation I chose on the left. Then comes lambda L. Then comes BL, sigma LB. then comes lambda L minus 1 to the power minus 1. And because I borrowed that, basically this lambda minus 1, because it's not present here, I have to put it back in after the end of my repeat unit, L minus 1, and then it continues like BL minus 1 sigma L minus 1 B harmlessly until you are at the end. Okay, that would be your guess, and it looks pretty horrible, doesn't it? Okay, but we can dramatically simplify it. Okay, the first simple step of simplification is that these guys cancel here. So the next thing is that I would say, well, up to here everything looks the way we want it to be. And here everything also looks fine. I mean, this is just the sequence of BL to B1. So the sort of like the location where we are sort of like worried about that it looks awful is basically just these 5 guys here. And what would we like to have? I mean, we would like to have a prediction where we have a nice EA L plus 1 matrix sitting here and some garbage in between, and to have a B L plus 1 matrix sitting here, because then we could argue what is sitting here is just what we are looking for, namely the structure of the state, which we take as a prediction. Okay, and how can we do that? So because this would then be sort of like, this would be the this here, so that's the psi guess for sigma L plus 1A, sigma L plus 2, L plus 1B, which are the 2 new sites which I added when I went to L plus 1 from L. The guess is simply lambda L, BL, sigma A, L plus 1, lambda L minus 1 to the power minus 1, A, L, sigma L plus 1B, lambda L. Who would have guessed that? But that's actually the right formula, but it gets a nicer form if you say, well, let's multiply these 2 guys together and then do one of these steps of left normalization. You remember from yesterday, we could have these matrices sigma and turn them into matrices A sigma with left normalization and some stuff, which I call a garbage G to the right. Or we could do something to these matrices like making them right normalized, which I call a matrix B, and have some other garbage to the left. You remember that from yesterday. I mean, that was one of the procedures I explained, how you change between normalizations. So this matrix, this product here is some matrix M. But with this trick, I can put it into that form that I say I turn that into a left normalized matrix, which I call now AL plus 1, sigma A L plus 1. Then there is this garbage. The garbage I call lambda RL. Don't ask me why. This is sort of like traditional notation. Then in the center I don't touch this guy here, lambda L minus 1 to the power minus 1. And then I have again here a matrix which has no special normalization properties. Now I use the second trick, and the gamma, the G tilde I call lambda L left, and then comes a matrix B, L plus 1, sigma B, L plus 1. And now this, of course, is nice in the sense that now I have A matrices up to side L plus 1 to the left. I have B matrices up to side L plus 1 from the right. And what I have to sort of like minimize in energy in an orthonormal system is this object here, and this is my guess to start with. I mean, this is something you can do in Python or MATLAB if you don't worry about efficiency. You can program this entire stuff which I just mentioned very quickly and try that. That definitely works. Okay, so this is our guess here. And that has sort of a neat structure. It looks at least sort of symmetric. Okay, so the speed up you achieve here is really dramatic. So the next and probably last thing for today, and meaning therefore for this school, and for the rest I refer to the already announced sort of like review lecture notes that we should have next week, is the second question: how can I build a thermodynamic limit state? Okay, we already know the answer. A thermodynamic limit state would be given by taking this unit and repeating it as often as you like. And sort of like, and then of course the spins that trigger the matrices, of course you then start with the first spin, the second, then the third, the fourth, the fifth, the sixth, and so on. You build up your system. So the infinite system, or the thermodynamic limit state, would then simply be given by A lambda B lambda minus 1 A lambda B lambda minus 1, where these lambdas of course not the same but the ones we have in the expression. And then you would have here sigma 1, sigma 2, sigma 3, sigma 4, and so on and so forth. And then you can do your evaluation tricks of working out overlaps and stuff like that. The question, of course, you may ask is, well, when can I stop? The thermodynamic limit, of course, is only reached strictly for infinite system size. For a gapped system, we know that being at some multiple of the correlation length will be big enough. But assume we know nothing about it, how can I get a signal from the method itself that I have iterated long enough to have a reasonable approximation to something I could call a thermodynamic limit state if I build it from these repeat units? And to do that, you need the following result. And I think we have the time, 10 minutes, that should be enough. If only I found my pages here. If you consider, perhaps later on, if you're interested, the bottom of what I wrote on pages D and then the top of page E is how do I get a reduced density matrix in a matrix product state. And because I'm working here in a mixed canonical representation, I'm only I'm giving you the result, which is that you just write down your state psi in a mixed canonical representation. Then you construct the projector psi, and you trace out the degrees of freedom on B or on A, the right-hand side or the left-hand side. What you find is, when you do that, and it's a simple calculation which you perhaps simply follow through, is that the reduced density operator for a system, half system of length L, on the left-hand side is given by these matrices lambda L times lambda L dagger. I mean, if these are singular value matrices, the dagger doesn't mean much, but for general matrices, lambda, the order matters. Of course, if you work out the reduced density operator on the other side, it's given by lambda L dagger times lambda L. And these are in these are in orthonormal bases which are formed from the products of these P's on the one side and the A's on the other side. This is one result which is useful. So this is number one. But another very interesting result, which I will need in a second, is the one when you calculate the same thing, not in a mixed representation, but we now decide on one where everything is, say, left normalized. So psi would be A, or something like that. And now you ask the same question, what would be rho A like? And then the expression becomes much more complicated. It does not simplify like this. It stays a long string of A matrices which you have to multiply together. But looking at the formulae which you get, what you can read off trivially is that the reduced density operator in a finite system from 1 to L, where sort of like I cut here at L minus 1, but I could also make the cut here at L. There's no need to be symmetric between left and right. But this is related to the one which you get if you make the cut here by a sum over sigma L, A sigma L, rho A L, A sigma L dagger. Sorry, I'm really simply running out of time here. But this is a very simple calculation, and I gave every step on these pages D and E if you're interested in following up on it. Okay, so this is a relationship which on a finite system is always strictly true. That's sort of like it's an exact mathematical statement. But what I could also argue is that I say, well, to say something about the thermodynamic limit, I could interpret that as a fixed point relationship, not just one which transforms it from one to the next on a finite system, but a fixed point relationship where I would say, okay, if these are the reduced density operators of my half systems, then we are really comparing the reduced density operator on, say, this system here to the one, I'm exaggerating now in the picture, to this reduced density operator here now. And you could not expect that this relationship would hold as a fixed point relationship unless you're essentially working in the thermodynamic limit, where whether there are L sides, L minus 1 sides to the right, or L or infinitely many, should not really matter anymore. It just matters that I say, if I look from the left-hand side, take L minus sides here, and compare it to L here, then this relationship holds because it doesn't really care anymore that it was originally only working on two systems of equal size, roughly speaking. So I would say I want this relationship to hold for the reduced density matrices I obtain in my calculation here, like this lambda lambda dagger. And if this holds to some accuracy, I would argue I'm in the thermodynamic limit. So I would argue the thermodynamic limit is reached if this relationship now holds. Sigma L, A sigma L, and I write now, instead of rho A L, I write now lambda lambda dagger, lambda L dagger, A sigma L dagger. And this should be equal to rho A L minus 1, but this is nothing but lambda L minus 1, lambda L minus 1 dagger. Okay, I mean, if these guys were defined on the same system, that would be strictly true always. But here we are really comparing two different systems, and so this is not at all clear that this will be the case. So, but what I can do to this relationship here now is I can transform that I do the typical trick of which I used here. Where is it? Here. I can transform an A lambda to a lambda B. So what I can write is, this is lambda L, which I already know, B L plus 1. And on the right hand side I get the same thing daggered. So I get B L plus 1 sigma dagger, lambda L dagger. So then at the right hand side I get this lambda L minus 1, L minus 1. So these guys drop out together with the sum, and I can introduce something which I call rho LL. just as the lambda dagger here, and ask the question whether this is the same as rho L minus 1, which I get from these guys here, following the expressions, sorry, it's this one, following these expressions here. And to measure the distance here, and this is basically where I will conclude, because if you know that, then you know that you have reached the thermodynamic limit. If they are equal to some very high accuracy, and one way of measuring that would be simply by calculating something like a fidelity between these guys, where you would look at the trace of the square root of rho L times rho times square root of rho L, where these rows are these guys I wrote here. And that sort of like somehow should approach 1, and somehow you have to agree with your conscience what you would accept as being essentially 1, and accept that as a thermodynamic limit state. There you really have to gain some numerical experience. One can actually show that evaluating this trace here is nothing but the sum of the singular values of this lambda L times lambda L minus 1 to minus 1, but this is not so important for the moment, so I just write down there's an easy evaluation of this expression. And from that you can actually judge whether you have reached the thermodynamic limit. Okay, so before I stop here, let me mention just what I could not cover and why I would like to encourage you to read either the lecture notes or this upcoming paper, which tries to explain the ITBD method, which is also using a repeat unit like that and doing time evolution just on that, and from there going right to the thermodynamic limit. It's sort of like it relates to what I have described now, just like time-dependent DMRG or TEBD relate to standard DMRG. It's the same thing, so you will recognize many of the arguments again. But I think Frank and others already mentioned quite a bit about ITBD in the context of IPEPs and other methods, at least the words. The second thing is, and this is the one thing which you should worry about and really read it up, is if you take these systems which I have just constructed and you say, I'm not really interested in the thermodynamic limit, I just want to build a big system, which I think is a good approximation, and I stay within this notation of A and B. You can evaluate expectation values very easily. If you wish, because you think it's more beautiful, you can left normalize everything, then you have A matrices everywhere, you can have B's everywhere, whatever. But for any of these questions, standard tricks of evaluating expectation values, as I showed them yesterday, they just work without any further ado. But the problem is, if you take this repeat unit here, and you continue it up to infinity, what you get is a sequence, as you can see it here, of A, B, A, B, A, B, which means that the orthonormality structure of the state, which allows you to operate, is simply lost. On a finite system, you would say that's no problem. If I wanted all A matrices, I start from the left, and I make them all A matrices, like with this trick here. But the problem is, on an infinite system, there is no starting point and there is no end point for that. So you have to come up with a different idea, and there is one which simply says these relationships must be such that if I want to calculate the expectation value of the unity, it should simply give you, of the unity operator, it should give you in the basis you're constructing here something like delta A prime. Please read it up in the notes, because from this you can then really take this infinite system size and evaluate expectation values very efficiently. If you don't want to study that, you simply stop at some L plus L, which is of your fancy, and do whatever you want with it, just in any finite system DMRG calculation. Okay, that's all before we get too entangled in all these indices. Thank you very much. Brief questions?
Yeah, so how do these infinite algorithms perform for particle systems?
For which system? For critical systems. Well, I mean, the point is, well, quite well. I mean, I would not say that they are, I mean, sort of like there's a priori no reason why they should be much worse than for gap systems. It's simply that the approximation to the thermodynamic limit will always be only approximate. But then you can, yeah, but that sort of like needs some sort of like further discussion. You can basically replace extra for the, if you take rows which you obtain for different system sizes. I mean, you can also say you bring them up to convergence in the various numbers of states, and then you can set up convergence procedures for that, instead of sort of like fixing it for 1L and making it as good as possible and then extrapolate the typical finite size extrapolation. But unfortunately for this question there is a few nice papers by people like Latorre and co-workers who discuss that in quite some detail. That's like not something I can give a hand-waving answer which would be meaningful.
So for the two-dimensional GPS, so is also get any GPS can just write down in this form, in lambda and is AB lambda?
No.
No?
No. I mean, of course you can do it formally, but then these matrices, I mean, this is an essentially one-dimensional notation. You can do it, but then they would blow up. They would blow up sort of like in the vertical direction. I'm not aware that anyone has tried. I mean, of course, there would be two-dimensional generalizations of the notation, but I'm not aware that anyone has tried with success so far then to come up with something like a prediction algorithm or how you would set up the repeat units. I mean, in principle, it's clear. I mean, IPEPS uses such a repeat unit, which would be the generalization of the typical ITBD or IDMRG repeat unit I have written there in a box. But to really set it up like as a fixed point relationship like here with a prediction, I'm not aware of that. Perhaps someone else has seen something like that, and at least I haven't.